Hello, AP Chemistry students. Today we're going to be finishing up Chapter 16 notes for acids, looking at first acid-base behavior, kind of, how to compare strong versus weak acids or stronger versus weaker acids, and then we'll finish up with looking at Lewis acids and bases. So again, we've already talked about, what's considered a strong acid, the 7 strong acids, what's considered a strong base, but this kind of looks at, molecularly why an acid is strong versus weak. And again, as we talked about with our Bronsted-Lowry definition of acids, an acid is something that is going to be able to donate a proton, donate hydrogen ion, and the more easily an acid can donate a proton is based on its bond type, how strongly that anion is able to hold on to the hydrogen ion. So that's what we're going to be looking at, and here it shows, again, a hydrochloric acid is considered a strong acid, but actually in terms of the other two binary acids, hydrobromic and hydroiodic, hydrobromic and hydroiodic are actually stronger acids than hydrochloric acid, and that's what we'll talk about here next. So the binary acids, which again the strong ones are hydrochloric, hydrobromic, hydroiodic, depending on their bond strength as well as their bond length, because again, longer single bonds are longer than double or triple bonds. The stronger the bond, the less easily it dissociates. So that's why hydrofluoric acid, even though it's in the same family as the other 3 strong binary acids, it is a weak acid because fluorine is so strongly electronegative that it does not readily give up the hydrogen ion. So it doesn't want to donate its proton because of how strong the electronegativity is of fluorine. And that's also why hydrobromic and hydroiodic are stronger than hydrochloric acid, even though hydrochloric acid is also strong, because their electronegativity is decreasing as we go down the column. So basically the strength of a binary acid is going to decrease, the bond strength of the binary acid is going to decrease as the size of the anion increases, which then makes, as we go down a column, makes a binary acid stronger as we go down the column, because again it has less of that anion, has less of a hold on the hydrogen ion, so it can donate the hydrogen ion more easily. So that means then that acidity increases as the size of the anion increases as well, and that's what this is showing you here, that as we go down the column, the size of the anion is increasing as well as its strength of its electronegativity is decreasing. So acidity is going to increase because of the anion's ability to hold on to that hydrogen ion is decreasing. So of the 3 strong binary acids, hydroiodic acid is actually the strongest, and then hydrofluoric would be the weakest, and hydrofluoric is just a straight up weak acid. Now the oxyacids, like what you see here, the different groups of chlorate ion, those contain OH bond. As you can see from all of these, here's the OH bond on all of those different oxyacids. And as the electronegativity of the nonmetal, in this case the chlorine is what we're referring to, as the electronegativity of the nonmetal increases, acidity increases. And Now that's obviously, these are all chlorine, so we can't really compare that, but if we were to compare chloric acid versus sulfuric acid or bromic acid or something like that, that's where we could compare the nonmetals electronegativity for the same reasons that we discussed up there. But in the case of the oxyacids, as we add more oxygens to the central nonmetal, in this case the chlorine, the acidity increases. And that's why in terms of our 7 strong acids, only chloric and perchloric are considered strong. Chlorous and hypochlorous are considered weak acids because they have fewer oxygens. And that's because as we add more oxygens to our central atom, that pulls the electrons more closely to the central atom, making the bond between the oxygen and the hydrogen weaker, so it can donate that hydrogen more easily. Where with the 2 weaker acids that have only 1 or 2 oxygens on them, they don't have the strength to pull the electrons more towards them as much as the other 2 do, so therefore they can hold on to that hydrogen bond. That bond between the hydrogen and oxygen is much stronger, so they don't donate that proton as easily. So that makes hypochlorous, HClO, the weakest, and perchloric acid, HClO4, the strongest. So again, as we add oxygens to the central atom, the acid gets stronger, meaning it can donate donate the hydrogen ion more easily, because the electrons have less of an attraction to the hydrogen ion, more of an attraction to the central atom. Then ternary acids, which I've always just kind of lumped oxyacids and ternary acids together, but ternary acids are when we have obviously more than one nonmetal in an acid, and it doesn't have to be oxygen, where oxyacids are with polyatomics that have oxygens in them. So again, the same trend, just saw misspelling, sorry. The more electronegative the non-metal, not known metal, non-metal, the stronger the acid. And again, it's for the same reasons as what I was explaining up here. The more electronegative the non-metal is, the more it will hold on to the other non-metal, and then making that bond between the other non-metal and the hydrogen a lot weaker, so that hydrogen can be more easily removed, which again is how we describe a strong acid, is it's able to donate or lose that hydrogen ion much more easily. So in terms of, again, comparing these acids here, HOCl, which is hypochlorite, so because chlorine is more electronegative than bromine or iodine, it's going to pull the electrons on the oxygen more towards it and weaken the bond between the oxygen and the hydrogens, so the hydrogen can be removed more easily. Where as we go down the column, electronegativity decreases. So bromine is going to have less of a pull on the oxygen's electrons. Same goes for iodine. It's going to have even less of a pull on the electrons of the oxygen. So that makes the bond between the oxygen and the hydrogens here stronger, so they can't donate that proton as easily as the HOCl. So again, the more electronegative the nonmetal is, the stronger it can pull the electrons towards it, weakening the bond between the other nonmetal and the hydrogen. So the more electronegative atom in a base the weaker it is, and that's for the same reason. So the same holds true for a base. Now remember though, electronegativity increases as we go up and towards the top right hand, towards fluorine, making fluorine the most electronegative element. So in terms of bases, as we go more towards fluorine, those bases get weaker and weaker, which, as we talked about, in the beginning of this chapter, the group 1 alkali metals and the heavier group 2 alkaline earth metals, those are stronger bases, again, because they have weaker electronegativities. Then carboxylic acids. So those are our organic acids, which have a carboxyl group. That's what this is showing here, the C double bonded O and then the OH. That's the hydrogen ion that gets donated when it is ionizing. And then here the R is just a side chain of whatever else, more carbons and hydrogens or anything else. But those are all fairly stable and are all considered weak acids. So again, none of those are strong acids. They're all considered weak. And then nitrogenous bases, those are organic bases where we don't see the hydroxide ion like we do in the group 1A's or 2A bases. But these are organic bases that contain nitrogen, which ammonia is one. Ammonia is not up here. But DNA and RNA, those are also made of nitrogenous bases, which you see here, the adenine, guanine, thymine, cytosine, and uracil. So those are different types of organic bases. And I really don't think you need to worry about those too much. Usually when they have a question using these bases on the AP exam, it's more about hydrogen bonding than about acid-base type stuff. But those are all weak. Again, the only strong bases are the hydroxides from column 1 and then the heavier column 2 hydroxides. So everything else is considered weak. Then finally, in section 11, Lewis acids and bases. These are just another way of looking at acid-base behavior, a different way to define what an acid or base is. Lewis acids, they are electron pair acceptors, which is complete opposite of a Bronsted-Lowry base. Remember, acid. Bronsted-Lowry acids, those are proton donors. They donate a proton. Here, a Lewis acid is accepting not a proton, but a pair of electrons. So what you want to look for to identify if this is a Lewis acid is, in order for it to be a Lewis acid, it has to be either a molecule or an ion that has an incomplete valence shell. It can have multiple bonds, or a central atom that can go beyond the octet, and that's our third period elements, again, that can do that. Second period elements cannot do that. But so they have basically an opening where they are able to accept a pair of electrons. So an example of a Lewis acid, let's see if I can do this in here, would be no, let me erase that. Pen, let me change my color. Let's go blue. There we go. So an example of that would be like boron trifluoride. Because if you're in a boron, that's a long bond there. Boron trifluoride, is an exception to an octet rule. It does a trigonal planar, and it's okay with just these 3 pairs of electrons, but boron does have an opening for a pair of electrons that it can accept. So it doesn't need an octet, but it does have room to accept a pair of electrons if it were provided those. So that would be considered boron trifluoride a Lewis acid. Really wish there was a better way to do this. Then Lewis bases are just the are just the opposite. They are electron pair donors. So they donate a pair of electrons. And in fact, all Bronsted-Lowry bases are Lewis bases, but not the opposite way around. So if they can donate a pair of electrons, then they can also be considered a Lewis base. And so they can donate a pair of electrons to something. It doesn't have to be to hydrogen ion. Anything that, again, like up here, the BF3, that any substance that can accept a pair of electrons, that has an opening, a vacancy, a Lewis base can donate pairs of electrons to. Oh, I thought I had, where'd we go? So to help identify a Lewis base, you want to look for molecules or ions that have an unshared pair of electrons. And in that case, with those unshared pair of electrons, they're able to donate those electrons to a Lewis acid that has an opening for that. Let's change colors here. So, for example, something like, where'd my pen go? Ammonia, NH3. And I find it easier to draw them out. I think it's easier if you draw them out so you can see who does have an unshared pair of electrons. You don't have to draw them out, but I just find it easier to do that. So by drawing out their shapes, you can then see here we have on ammonia this unshared pair of electrons. So because it has this unshared pair of electrons, it can donate those electrons over here to boron trifluoride's vacancy. So that makes ammonia, which is also a Bronsted-Lowry base, but it also makes ammonia a Lewis base as well. So then after it donates its protons to boron trifluoride, we end up with a compound that looks something like this. Hopefully this will let me draw it. Yeah. That's supposed to be an H. And then let me change colors here for the bond between them. Let's go orange. So here's the bond that shows nitrogen has donated a pair of electrons to boron. And this is actually called what we refer to as a coordinate covalent bond. So that is known as a coordinate. That's supposed to say coordinate. And a coordinate covalent bond is where both pairs of electrons come from the same element. Where normally in most covalent bonds, one electron comes from one element and one electron comes from the other that they share in the bond. But in this case, both of these electrons here came from the nitrogen. So that's the other thing you can look for is if you draw out the structures of a compound that's already formed, you can look for where did two electrons come from the same element, where was there a coordinate covalent bond, and that shows then that we have a Lewis acid-base situation. All right, so go ahead and make sure you've submitted the homework from the other day. I will post the key for that later on over the weekend, so you can check that, since I'm not going to be able to get it. Well, yeah, I'll probably post the key on Sunday, so you can look at that and use that to study from, and then complete the corresponding worksheet for this lesson, and that will be due next class time. So have a good day and enjoy your weekend.